Hey everyone, welcome to this explainer brought to you by Forge College. So in our last session, we kind of decoded the mysteries of address types and formats. We looked at how different addresses actually look and function. But today we're going to literally unroll the engineering blueprint of a Bitcoin transaction. We're going to connect what we learned about those address types to the actual raw bytes flying across the network. Now I know, looking at raw bytes usually makes people's eyes just totally glaze over. But honestly, don't worry, we're going to make this completely painless. It's kind of like taking the sleek outer shell off of a sports car just to check out the pistons and gears. Okay, so here's our schematic roadmap for today. We'll start with the blueprint, look at pointers, locks, and proofs, then dissect the wire format. After that, we'll do a P2WPK walkthrough and wrap it up with the final assembly. Let's dive right in. Section 1. The blueprint, inputs and outputs. Let's start with the big picture here. You know, one of the absolute most common misconceptions about Bitcoin is that it works like a traditional bank account, where some central ledger just tallies up your balance. But in reality, Bitcoin transactions are actually mechanical engines. They don't use account balances at all. Instead, they literally consume previous outputs to create brand new ones. So it's less like transferring money between checking accounts, and honestly, a lot more like melting down old gold jewelry to cast completely new coins. Notice the structural difference we've got here. On the left, an input references exactly where the funds came from using a transaction ID and an output index, and it carries the unlocking data, basically a digital key. On the right, an output sets the new locking logic, so who gets to spend it next, and it specifies the exact value in Satoshis. So inputs look backward to prove you have the funds, while outputs look forward to lock them up for the next person. All right, Section 2, Pointers, Locks, and Proofs. To make sense of these highly technical fields without getting completely bogged down in raw hex code right off the bat, let's use a mental model. Think of a transaction as a bundled schematic of three very specific things: pointers, locks, and proofs. First up is the pointer. Officially in the code, this is called the out point, and its job is extremely simple but absolutely critical. It just points to the exact previous transaction and the specific output within that transaction that you want to spend. It's literally a crosshair targeting a specific unspent transaction output, or UTXO, on the blockchain. Next, we've got the lock, technically known as the scriptPubKey. This little guy lives in the outputs. It's essentially a cryptographic puzzle that just persists on the blockchain, sitting there, waiting for someone to come along with the right key. When you send Bitcoin to a friend, you're basically creating a new lock that only their private key can open. It's not really like a standard padlock, though. It's way more like an intense cryptographic escape room that only accepts pure math as the key to get out.
And finally, we have the proof. This is the unlocking data you provide in the input to actually satisfy that lock. Now, depending on the transaction type, this proof might live in the scriptSig field or maybe in a separate witness stack. But its purpose is always exactly the same: to prove to the network that you have the right to spend those funds. So think of this whole relationship as a triad. The pointer finds the exact safe you want to open. The lock is the heavy steel door on that safe. And the proof? That's the exact mechanical combination you spin to crack it wide open. Moving right along to Section 3, Dissecting the Wire Format.
Okay, so we have our pointers, locks, and proofs. Now let's look at the actual wiring of this machine. We call this the wire format, which is the exact order and binary encoding used when a transaction is broadcast across the Bitcoin network. And let me tell you, Bitcoin is notoriously unforgiving. If a single byte is out of place, the network will reject the transaction entirely. No exceptions. It's exactly like trying to build a piece of IKEA furniture, but you're missing a screw, the whole thing just falls apart. Looking at the top-level fields here in their mandatory order, we start with the version number, followed by the input count, the actual inputs themselves, then the output count, the outputs, and finally the lock time. This sequence is absolutely crucial because Bitcoin network parsers read these bytes deterministically. They're not looking for helpful labels or tags. They are blind parsers that literally just count bytes. If your input count says you have 2 inputs, the parser blindly expects the very next chunk of data to represent exactly 2 inputs.
And the precise encoding within those fields? It matters immensely. Numeric fields like the version and lock time use what's called little-endian encoding. You can think of little-endian in kind of a fun way. It's basically like reading a book from right to left, where the least significant byte actually comes first. For counts, we use a special variable length integer format called a VarInt, and scripts are always length-prefixed. That means you have to state exactly how long the script is right before you provide it. This is hyper important because, well, you really don't want that blind parser accidentally reading a cryptographic signature as a Bitcoin amount. Misreading a VarInt length or a little-endian numeric field won't just cause a minor glitch, it will literally break the transaction's signature algorithm, making the whole thing instantly invalid. No way around it.
All right, Section 4, the P2WPKH walkthrough.
Abstract rules are great, sure, but practical examples are really what make these concepts click. So let's take everything we've just talked about and walk through a real-world SegWit example. A pay-to-witness public key hash, or P2WPKH transaction. Notice how the serialization order builds specifically for this format. It starts with the 4-byte version, but then it inserts a special marker and flag byte, a 0 and a 1. Think of this kind of like a VIP wristband that tells the network, hey, this is a SegWit transaction, so treat it accordingly. Then we get the inputs and outputs, just like the legacy format. But check out step 4, the segregated witness data. And finally, step 5, the lock time. Now, the absolutely crucial design choice here is exactly where that witness data is placed. As you can see, the witness area appears after all the core outputs. This specific placement is the absolute key to SegWit, because the unlocking signatures, the bulky witness data, are appended entirely after the core inputs and outputs. They don't change the legacy transaction ID. This was a massive, elegant design choice that effectively fixed a major historical issue in Bitcoin called transaction malleability. Think of malleability like someone secretly changing the serial number on your personal check right after you already signed and handed it over. By segregating the witness data to the very end, that problem just completely vanishes. Pretty clever, right? So when a node receives this perfectly ordered bundle of bytes, how does it actually verify it? Well, first, it computes the signature hash. It follows the BIP 143 standard, which defines exactly which fields are included in the hash. Next, it verifies the actual cryptographic signature found in that segregated witness stack against the provided public key. Finally, it ensures that the hash of that public key perfectly matches the lock, the witness program, that was specified in the previous output being spent. To put it simply, it checks the pointer, it verifies the proof, and it unlocks the lock. The whole shebang.
Section 5, the final assembly.
Okay, we've laid all the parts out on the workbench today. We've looked at the inputs and outputs, the encodings, and the precise order of operations. So let's quickly summarize how this structural blueprint fits together before we wrap up. I want you to remember 3 core engineering principles here. First, encoding details absolutely matter. Whether it's little-endian or VarInt, these dictate the exact byte ranges parsers use. Second, script placement determines what gets signed and what is malleable, just like we saw with the SegWit witness data. And third, serialization order is strict and completely unforgiving. There is literally zero room for interpretation in the wire format. Breaking even one of these rules results in a completely failed transaction, which essentially burns all your hard work.
So as we prepare for the next step in this module, which is building raw transactions entirely from scratch, I really want you to ask yourself, how will you apply these strict byte encodings to build a perfectly valid signing context manually? Understanding the blueprint we just covered is really the only way you'll be able to confidently construct a transaction that the Bitcoin network will actually accept.
And that brings us to the end of our schematic review. Thanks so much for exploring this engineering blueprint with us in this explainer brought to you by Forge College. If you found this breakdown helpful and you want to learn more, definitely be sure to visit forge.college to dive much deeper into this subject, explore our full courses, and keep building your Web3 knowledge. Until next time, keep learning and keep building.